Oxidation-reduction reactions are another type of chemical reaction. These are characterized by the transfer of electrons. Electrons are transferred from one reactant to another. They're also called redox reactions because oxidation reduction is really long, especially when you have to write it out. Many redox reactions involve oxygen. Here are some examples involving oxygen. So a metal such as iron can react with oxygen and form an iron oxide. That's rusting. Combustion, where we have something like octane reacting with oxygen to form carbon dioxide and water. That's an oxidation reduction. Here's a nonmetal reacting with oxygen to form water. Those are all examples of redox reactions. Here's a more detailed picture. Here's a balloon filled with a mixture of hydrogen and oxygen gases. And if you get that reaction started with, say, a candle, you get kablooey, and this unfortunately doesn't last very long. It's over very quickly, but here's a picture we can look at. It forms water, and that's a redox reaction. Here's one that happens without oxygen, without combustion. Sodium, metal, and chlorine gas will react and form sodium chloride. Here we can see, when we look at these reactants and products, we can get a better idea of what's going on here. What kind of a compound is sodium chloride?
Solid, or it's aqueous, or it can be.
It can be aqueous. It is a solid. It is also soluble in water, but molecular ionic acid. It's ionic. And so we have ions here. We did not have any ions over there. How does something become an ion? By gaining or losing electrons. So here are two examples of sodium reactions, sodium reacting with oxygen and with chlorine. Both of these are a metal with a nonmetal. Reactions of metals and nonmetals are typically redox reactions. So here's the sodium reacting with the oxygen, and this looks kind of funny, doesn't it? Kind of messy there. That's because we're showing the charges in the chemical formula, and that messiness tells us why we don't usually do that. It's hard to look at. But trying to point out that these are sodium ions, and over here we had sodium atoms. The sodium became an ion by losing an electron, and who gained the electron? The oxygen atom. Okay, it's easier to look at with the chlorine. Sodium lost one electron and gave it to chlorine. Now we have sodium ions and chloride ions. So that's the transfer of electrons. Yeah, I always get ahead of myself. So I kind of already said all of this. What is important to understand is that if one atom loses an electron, or more than one electron, another atom has to accept them. You can't just leave electrons on the side of the road, dump them in a canal behind your uncle's farm. You have to give them to someone else, okay? And if you're going to gain electrons and become an anion, those electrons have to come from somewhere, and there's no bank where you can go and check out some electrons, or a library or something. They have to come from another atom or ion. So oxidation and reduction always go together. So we have to be able to identify which is oxidation and which is reduction. Oxidation is loss of electrons, reduction is gain of electrons. And this mnemonic oil rig is a good way to remember that. Oxidation is loss, reduction is gain of electrons. So when we look at the sodium atom here, it became a sodium ion by losing an electron. Oxidation is loss of electrons. The sodium was oxidized, the chlorine was reduced. If there's an oxidation, there has to be a reduction. When we make ions, we've got a complete transfer, but we can also have an oxidation-reduction reaction where the transfer of electrons is not complete. We just have a shift of electron density, where it went from maybe equal sharing to not so equal sharing. And we looked at water molecules when we talked about how things dissolve in water and saw how that electrons are not always shared equally, right? So in a hydrogen molecule, we have two identical hydrogen atoms. They're going to share the electrons in their bond equally. And the same for the two chlorine atoms in a chlorine molecule. But when this reaction occurs and a hydrogen chloride molecule forms, the chlorine is going to hog the electrons, is not going to share equally with the hydrogen. That results in an electron density shift. And so this side of the molecule becomes partially negative. It's not an ion, but it's getting closer. And this side becomes partially positive. Okay, so how do we keep track of or figure out, just by looking at the equation, which one gained electron density and which one lost it? We don't have ion charges to look at. We'll look at that in just a second. So we do have reduction is gain of electrons or increase in electron density. So the chlorine was undergoing a reduction because it gained electron density. It didn't become an ion, but now it's got a bigger share of the shared electrons, and the hydrogen was oxidized. Any questions? Well, looking at nonmetals especially, it can be hard to tell what's being oxidized and what's being reduced. And so we use a tool called oxidation states to help us figure that out. Oxidation states are imaginary charges assigned based on a set of rules. Okay? There is good science behind the rules. Thankfully, we don't have to understand that. We can just follow the rules. So oxidation states are just numbers that we assign to each atom in a reaction so that we can track how the electrons are moving around. Oxidation states are not ion charges. They're imaginary. Ion charges and oxidation states are often the same, especially for metals. They're generally going to be the same number, but you just need to understand that they are not ion charges, okay? It can be confusing. So here are the rules for assigning oxidation states. And you'll see that many of these fall along the same lines as how do we predict the ion charge. So free elements have an oxidation state of 0. Anything in its elemental form, whether it's a monatomic element or a diatomic element, it's going to have an oxidation state of 0. If you have monatomic ions, like sodium ion, in NaCl we have Na plus and we have Cl minus. Na plus has an oxidation state of +1 and the chloride is -1. Just like with ionic charges, all of the oxidation states for the atoms in a compound have to add up to the overall charge, which would be 0. So in sodium chloride, +1 and -1 add up to the overall charge, which is 0. If you have a neutral molecule, this is kind of redundant with the compound, they add up to 0. If you have a polyatomic ion, the oxidation states add up to the overall charge on the ion.
Complex. Jerks.
Yeah. He's tooting his own horn. Yeah. Okay. In their compounds, metals are always going to have positive oxidation states because they form positive ions. The group metals are going to have a +1 oxidation state. They have a +1 charge. The group 2 metals have a +2 charge. They have a +2 oxidation state. So far everything is coinciding with charges, and that's why it's easy to get oxidation states confused with charges. But what about the nonmetals? In a compound of nonmetals, a molecular compound, there aren't any ions. And so how do we decide which one has more of the electron density? We just follow this set of rules. They go in order: fluorine, hydrogen, oxygen, then group 7, group 6, group 5. And these are the oxidation states. My pointer is being very slow today. These are the oxidation states that those will have. Now look at this with me. If fluorine is an ion, what's its charge? 1 minus. Hydrogen as an ion, what is its charge? Plus 1. Oxygen as an ion. 2 minus. Group 7 elements. 1 minus. Okay, so these oxidation states are the charges that those elements would have as ions. Okay? But the thing is, in a molecular compound, two nonmetals, they both want to have negative charges, but they can't both have negative. One of them has to be positive. And so this is the order of who gets what they want. That's how I think of it. Fluorine gets first dibs, then hydrogen, then oxygen, then anything in group 7, group 6, then group 5. So you have to remember the order. That's the hard part. The oxidation states are easy. They're the same as the charges. Have you guys had pho? Not fun, but pho. What is it?
It's kind of gross.
Kind of gross?
Amazing.
It's amazing.
I mean, it looks like somebody just.
It's Vietnamese, like noodle soup, right? It's like noodles and all this tasty stuff, right?
Texture.
Well, you see.
Well, I mean, it depends. Like, if you get the wrong kind, it's got like intestines and muscle.
Yeah, I think that's kind of what I had.
Yeah, don't get the regular kind. That's like sushi, right? You know, some sushi's awesome and some sushi's gross. It depends.
Sushi. All sushi is awesome.
Even the sashimi, the raw fish.
Yeah. Sam's
Okay.
the best when you look out.
See, a lot of people think that's gross, so you're weird. You don't like pho, but you like sashimi. Whatever. Okay.
It's okay. It's the eggs that we're eating.
Salmon?
Like, when they put the eggs on top.
They just kind of pop my heat on this one. Like,
My husband and his brother used to fight over the eyeballs in cooked fish. They would eat them.
yeah, I'm not big into it.
Like, okay, that was a fun diversion. Here, pho. We're going to come back to this. So pho is spelled P-H-O, and this doesn't quite work, but it's really close. What if we just skim off the end of the F? F-H-O, okay? And it makes the F sound. So this is how I remember it. Pho 765. So fluorine, hydrogen, oxygen. Fluorine, hydrogen, oxygen, then it's just 765 backwards up the periodic table. Okay? And there are examples given here. Let's look at,
So when you say orders and priority and what else?
when you have to choose between two things like here, CO2, oh, that's maybe not a good example. I don't like any of these
Which
examples.
element has the
Well,
oxidation
let's just try CCl4, okay? So we ask ourselves, you know, is there pho 765? So there's no fluorine, there's no hydrogen, there's no oxygen. We get to group 7. Oh, chlorine's group 7. That tells us, because we have two nonmetals here, we have carbon and chlorine. Chlorine gets to be what it wants, which is an oxidation state equal to the charge it would have as an ion. So the chlorine gets to be -1.
Okay.
And then we go to the rule that all of the oxidation states have to add up to 0. So what's the carbon going to be? +4. Okay. So that's what the list of priorities is about. The one that comes first gets to have the oxidation state equal to the charge it would have as an ion. And sometimes there's 3 or 4, and so you go in order, and then whoever's last ends up being positive. We'll do some examples. Fractional oxidation states are possible. Fractional ion charges are not possible. You can't have a half charge. Because how can you have half of an electron? It's like having 2.5 children. Which half do you have? How do you cut up a child? You don't. You have 2 children or you have 3. And then I'm not going to try to trick you on this. I just want you to be aware why things are the way they are. For oxidation states, we write the sign before the number, and for ionic charges, we write it after. So I'm not being random. There's a reason behind that. So that's why these are -1 + 1 instead of 1 - 1 +, etc. Let's look at the examples. Assign an oxidation state to each atom. Okay, so Cr. 0. It is an element. And elements don't have charges, so the oxidation state, again, lines up with the charge, 0. How about chromium ion, chromium 3? What's the oxidation state? It's the same value as the ion charge. It's +3. It's all by itself. We're looking at atoms individually when we're talking about oxidation states. Oh, I already did that one. Let's do a different one. Let's do PF3, because I already did CCl4 by accident. So there's 2 elements. This is a molecular compound. There's no charges. So then we say Fe765. Oh, fluorine. What would fluorine like as its oxidation state?
-1.
Yep, -1. So fluorine has an oxidation state of -1. And then phosphorus has to take up the slack. And what's phosphorus going to be?
+3.
+3. There are 3 fluorine atoms. There is absolutely no reason why one of them should have a different oxidation state than any of the others. They're all going to be the same. They're all -1. And so for the oxidation states to add up to 0, the phosphorus has to be +3. How about SbBr2? What's the oxidation state for the strontium?
+2.
Yep, +2. This is an ionic compound, so you can just look at the ion charges. So strontium is a monatomic ion. It's going to be +2 because it's in group 2. It's always +2. How about the bromine? -1. It is an ion here. Bromide ion. So if you have monatomic ions, oxidation state, ionic charge, the same number.
Did you get the SR to be +2 from the periodic table?
Yes, I got the SR to be +2 from the periodic table, because we learned to predict that group 1 metals form +1, group 2 metals form +2 ions, or 2+ ions, right? When it's ionic, when it's a monatomic ion, is just the charges. We'll see here an example F. This is a polyatomic ion. We have to do this one a little differently because we can't just say that it's -1, because there's 2 different kinds of elements in there. Let's do SO3 first. 2 nonmetals, Fe765, phosphorus, nope, hydrogen, nope, oxygen. What would oxygen like?
Be -2 and S would be +6.
Yeah, oxygen will be -2, because that's the charge it would take as an ion. And then sulfur has to make up the difference so things add up to 0. We've got 3 -2s, that's -6. There's 1 sulfur, it's got to be +6. This is the same mathematical concept as finding the charge on a transition metal from the formula of the compound. So let's look at NO3. Minus. This is nitrate ion. Fe765. Fluorine, nope. Hydrogen, nope. Oxygen. There's oxygen all over the place. Oxygen wants to be -2, and it's got dibs, so it gets to be -2. What's the nitrogen?
Is it +5?
It's going to be +5. The formulas here are similar, SO3, NO3. The difference is this has a charge, it's a polyatomic ion. So our oxidation numbers have to add up to equal the charge. So 3 negative 2's is negative 6, and a positive 5 adds up to negative 1. Any questions? Yes?
Why is it a positive 5 for the 9?
Well, we have 3 oxygens. They're each negative 2. And we have 1 nitrogen. And so if we add these numbers up, minus 2 and minus 2 and minus 2, that's minus 6. And if we add 5 to minus 6, we get minus 1.
Oh, wait.
And that's the charge. Any other questions? So oxidation is a loss of electrons, or we can also say that it's an increase in oxidation state. It's 2 different descriptions of exactly the same thing. Reduction is a decrease in oxidation state, or a reduction in oxidation state. Right? The oxidation state gets reduced. That's a gain of electrons. So when we look at 2 nonmetals reacting, carbon and sulfur, over here as reactants, they are elements and their oxidation states are 0. When we look at carbon disulfide, sulfur gets priority, it gets to be minus 2. The carbon has to be plus 4 so that the oxidation states add up to 0. Then we can look at what has happened to the oxidation states. Carbon has gone from 0 to plus 4. That's an increase in its oxidation state. It's oxidized. Sulfur has gone from 0 to minus 2. That's a decrease in the oxidation state. That's a reduction. How is it plus 4? Because there's 2 sulfurs. Whoops. So 2 sulfurs, each minus 2. And then this would have to be plus 4, so they'll all add up to 0. Yeah. So the oxidation states are not charges, but they act so much like charges. And if you have trouble remembering this definition with the oxidation states, you get the oxidation states, pretend they're charges. How do you go from a neutral atom to a minus 2 ion? By gaining electrons. Oil rig, reduction is gain of electrons. The sulfur hasn't become an ion here, but it has gained electron density. Questions? Use oxidation states to identify the element that is oxidized and the element that is reduced in the following redox reaction. So we need to look at every element and identify what the oxidation state is. Some of them are easier than others. That first one, tin, SN, 0. I'm going to skip HNO3 because that one looks messy. You don't have to do them in order. How about this guy? This is ionic. That's a little easier. This is an ionic compound. So oxygen is actually an ion. What's the charge of an oxide ion? 2 minus. So its oxidation state is going to be minus 2. What's the charge on the tin ion? Plus 4. So 4 plus technically. So the oxidation state is plus 4. We figure out the charge on an ion like tin the same way that we figure out the lower priority oxidation states. Let's do NO2. 765, oxygen wins. Oxygen gets to be minus 2. What does nitrogen have to be? Plus 4.
Do you pay attention to how many moles?
That's a good question. What about this 4? This is just telling me I have 4 of those molecules. I'm going to look at one molecule.
Okay.
In one molecule, I have 1 nitrogen atom and 2 oxygen atoms. Each oxygen atom has a minus 2 oxidation state. That's a total of minus 4. That means the 1 nitrogen must be plus 4 in its oxidation state. H2O, Fa765. Hydrogen wins here. What does hydrogen want to be? +1. And so then oxygen has to take up the slack. What's oxygen going to be? -2. Ooh.
Kind of gets what it wants.
It gets what it wants. They're both happy. Is water a stable compound? Yeah, it's really stable. Both of the elements in there have their preferred oxidation state. That's a clue about stability. Okay, let's go back to that messy one. So this is nitric acid. We have 3 nonmetals, Fa765. Who's got first priority? Hydrogen. Hydrogen gets to be what it wants, +1. Next priority is oxygen. Oxygen says, I choose -2. That's my favorite number. What does the nitrogen get? +5.
Oh, because you got the hydrogen taking the other.
Yeah, so you might want to write this out. So I've got +1, and I've got 3 times -2. And then I've got my unknown, my x, and that has to add up to 0. So this is -6 and +1, and x is 0. And so these two together are -5. X must be +5. However it makes sense to you. There's like too many ways to do a problem like that. That kind of math is not hard. It can be confusing though, especially in a stressful situation like taking an exam. You kind of lose your brain and you forget what a negative is. So we've identified all the oxidation states. Now we're going to look and see which ones have changed. I like starting at the beginning. So here's tin. It goes from tin with a 0 to tin with a +4. So that was a change. Let's see what's hydrogen. Hydrogen's going from +1 to +1. It was neither oxidized nor reduced. What about the nitrogen? +5 to +4. That's different. So nitrogen goes from +5 to +4. Oxygen goes from -2 to -2 everywhere. So there were 2 atoms who changed their oxidation states. It's possible to have more than 2 change. It's not possible to have only 1 change. If there's an oxidation, there has to be a reduction. So it always comes in pairs. You have to have 2 minimum.
So the ones that changed are those that oxidized.
One is oxidized, one's reduced. And so we look at how they change. This one went from 0 to +4. Oxidation is an increase in oxidation state, or oxidation is a loss of electrons. They'll give you the same answer, different ways of remembering. Here, tin's gone from 0 to +4. It goes to a +4 ion by losing 4 electrons. So that's the oxidation. I'm just going to call it ox. So tin is oxidized. And look what tin ended up with. Tin ended up with oxygen. That happens a lot. The thing that's oxidized is now in a compound with oxygen. And that goes back to the original way that word was used. And then the thing that's reduced is the nitrogen. Not the nitric acid, the nitrogen in the nitric acid. So nitrogen is reduced.
Do you have an example of a compound where, based on the Fa765, something gets its way and something does not get its way?
Sure. That's a good question. An example of a compound where one of the elements doesn't get what it wants according to the, with those rules.
According to the firstborn child rule?
Yeah. So sulfur hexafluoride is a real compound. Fa765, fluorine wins. Fluorine gets to be -1. What's the sulfur? +6. What did sulfur want to be? -2. So it didn't get what it wanted. Any other questions? You have to have oxidation and reduction occurring simultaneously, because electrons are transferred and one has to give them up and the other has to take them. Okay, so as if all of that wasn't confusing enough, we have to introduce agents. So let's talk about movies for a minute. So in Hollywood, there are movie stars and there are movie agents, right? Who's actually in the movie? The movie stars, right? They're doing the movie, they're doing the acting. What does the movie agent do? It gets them the job. So the movie agent causes the movie star to star in the movie, right? So the reducing agent doesn't get reduced. The reducing agent causes something else to be reduced. The oxidizing agent causes something else to be oxidized. If you're causing something to be oxidized, that means that you're being reduced. If you're causing something to be reduced, that means that you're being oxidized. So the reducing agent gets oxidized, the oxidizing agent gets reduced. I didn't make this stuff up, so you can't blame me. Determine whether or not each reaction is a redox reaction. And for those that are, identify the agents, the oxidizing agent and the reducing agent. And I guess I should probably point this out. The reducing agent contains the element that's oxidized. So back here when I said it was the nitrogen that was being reduced, the nitrogen is the thing being reduced. So nitric acid, the whole thing, the whole compound, is considered the oxidizing agent. Because you can't add just the nitrogen in the nitric acid. You have to add nitric acid, but it acts as an oxidizing agent. So let's look at these. There are different ways that you can identify whether it's a redox reaction or not. The certain way that's probably the most tedious is assign oxidation states to everything in there and see if anything's changing. Kind of shortcut ways, if you see something reacting with oxygen, probably a redox reaction. If you see a metal reacting with a nonmetal, probably a redox reaction. So here, just looking at metal and nonmetal elements, I'm going to predict that's a redox reaction. What are the oxidation states on these things? What's lithium? 0. How about chlorine? 0. And in lithium chloride, what are the oxidation states? Lithium's +1 and chlorine's -1.
Why is chlorine 0?
Here chlorine is 0 because it's an element.
Oh, no.
Because it's the lowest, when you're low, you're a 0.
Yeah, when you're a 0.
That's what Valentine's Day is all about.
That's awesome. Okay. The other way you can think of that is, okay, that's a neutral molecule, right? The oxidation numbers of the two atoms in the molecule have to add up to 0. You're not going to convince one chlorine to be +1 while the other's -1. They say, no, we're the same, we need to have the same. And so they both have to be 0. There's a lot of bickering in chemistry land. They resemble children in many ways. It's not the happiest place on earth.
Your place is the happiest.
Well, they say Disneyland is the happiest place on earth. I haven't been there for a very long time, so maybe that's my problem. So is this a redox reaction? Yes. So it is a redox. So we need an oxidizing agent. I'm going to call it OA. Who's the oxidizing agent? It's the thing that's being reduced. Reduction is gain of electrons. Chlorine. So the Cl2 is the oxidizing agent. I particularly like the reduction being a reducing of the oxidation state. So I look here and I'm like 0 going to -1. That's a reduction in status, or however you want to think of it. So what's the reducing agent? The lithium. The lithium is being oxidized. It's going from 0 to +1. It does that by losing electrons. Oxidation is loss of electrons. Questions?
Is that A1? R, A.
Oh, those are decimal points, periods. Sorry. For reducing agent and oxidizing agent. Yes?
When we're stating the oxidizing and reducing agent, are we always going to take whatever it is in the reaction?
It's always going to be one of the reactants, yes. The oxidizing agent or the reducing agent is always a reactant. And we look at the lithium here, we say during the reaction, the lithium is oxidized. I always have to think through that. The lithium is oxidized. So here the lithium has been oxidized. It can't act as an agent over here. These are the agents are going to be the reactants. Okay, number 2, is that a redox reaction? Are ions changing charges? Yeah. Here we have neutral aluminum. And then we have Al3+. That can only happen by changing electrons. This is a net ionic equation, and it's a lot easier to see what's going on there. What's up with that pointer? It's got a mind of its own. Okay, so this is a redox reaction. Who's my oxidizing agent? Oxidizing agent is the thing that gets reduced. So the oxidation number has to go down. Tin. So the oxidizing agent is the tin 2+, because that's what the reactant is. It's going from a +2 charge to a 0 charge, an oxidation state of +2 to 0. That's going down. It's losing electrons. No, it's gaining electrons. Reduction is gain of electrons. The thing that's reduced is the oxidizing agent. Right? The only way I can remember this stuff, and I've been doing this for longer than many of you were alive, the only way I can do this is to talk it through in my head. Oil rig. Oxidation is loss of electrons. Okay, that thing is oxidized. It is the reducing agent. Okay? So if your lips are moving during the exam because you're talking to yourself, that's fine. Unfortunately, I can't let you speak out loud, okay? But feel free to whisper to yourself.
So that reaction there, number 2, is that
This is the net ionic equation, yeah. There has to be some cation, some spectator ion, an anion floating around, but it wasn't actually participating, and so left it out. So what's my reducing agent then? The aluminum. Redox reactions can be very powerful, and so if you start looking around at warning labels and stuff, you'll sometimes see strong oxidizer or something like that, and that tells us that that's going to be very reactive, and we need to be careful with it. Okay, equation 3, is that an oxidation-reduction reaction?
brilliant. We have to decide oxidation states.
We have to look at oxidation states. Well, how about let's just start with the ions and look at their charges, because that's easier. What's the charge on this lead ion?
2.
+2. So its oxidation state would be +2. Let's leave nitrate alone for a minute. Because look, did anything happen to nitrate? We've got nitrate over here and we've got nitrate over there. Nothing happened to it. How about the lithium? What's the charge on lithium and lithium chloride? +1. And we see nothing's happening with the chloride. Somebody's having trouble in the hallway, though. Coughing up a lung. Okay, so over here we have lead and lithium. What's the charge on this lead ion? +2. And what's the charge on this lithium ion? +1. Did either of those change? No. There are ions here, but all they're doing is swapping partners. This is a precipitation reaction. There's no redox. You could go through and assign the oxidation states for the chlorine and the nitrogen and the oxygen. You'll find that they all stay the same. Okay, this one at the bottom, carbon plus oxygen to give CO2. Yeah, it kind of has to because it's a combustion reaction. And if we look here, this carbon is 0 and the oxygen is 0 because they're both elements. And in CO2, what are the oxidation states?
Oxygen's -2, carbon's +4.
Oxygen's -2, carbon's +4. So something happened. Carbon went from 0 to +4. Is that oxidation or reduction?
Lost electrons, so it's reduction, and carbon is the oxidation agent.
Did carbon?
Lost electrons.
Yes.
It's the oxidation agent.
Okay.
No.
Carbon has,
Wait.
in our pretend world, has lost electrons. Oxidation is loss of electrons.
Yes.
Oil.
So it's the reaction or reduction.
Yeah. So this is our oxidation. So carbon, this is redox. First, let's do that. Our oxidizing agent is the thing that's being reduced. Our reducing agent is the thing that's being oxidized. Carbon's being oxidized. I was looking at the oxidation state is increasing, that's oxidation. And then oxygen is going from 0 to -2. That's a reduction in oxidation state. It would be a gain of electrons. Reduction is gain of electrons. That's our reduction. The thing that's reduced is the oxidizing agent.
Carbon gained electrons.
Carbon went from 0 to +4. If that were a charge, you would get a +4 charge by losing 4 electrons. Those pesky negatives. It's not that we, yeah, it is confusing. Question?
How did you figure out PB was +2 in that?
How did I figure out PP was +2 in equation 3?
NO3 is -1.
NO3 is -1? Yeah.
forgot where it's-
Yeah.
I think that-
Previous
Yeah.
chapter, right? Yeah, nitrate is -1, and there's 2 of them. And so the lead is +2.
I just forgot that one.
Yeah, it's easy to do. Any other questions?
Why did we do this?
Why?
Why do they have such awful names?
I don't know exactly why they have such awful names. I will tell you this is not the end of confusion about pluses and minuses.
Great, I'm so excited.
In 1B, you'll get to cathodes and anodes. And there's oxidation and reduction involved at cathodes and anodes, and one electrode's positive and one's negative, and it's not the same as anions and cations, and it's just a mess. So at least we're not doing that yet. You'll have some time to recover before you have to do that. Okay, so combustion reactions are redox reactions. combustion reactions always involve oxygen as a reactant. Think about what is necessary for something to burn. Oxygen. It needs air, right? Well, what it needs in the air is the oxygen. Combustion reactions also emit heat, which is why we use them. Natural gas, we burn it to give off heat to cook our food or heat our homes or whatever. So here is the reaction, methane reacting with oxygen. When we have hydrocarbons with just carbon and hydrogen, or hydrocarbons containing oxygen, and in a combustion reaction, the products are always exactly the same, CO2 and water. So when this reacts with oxygen, it forms CO2 and water. We can look at what's going on with the oxidation states here. Carbon has gone from -4 to +4. The hydrogen stayed the same. The oxygen went from 0 to -2. The oxygen is gaining electron. It's reduced. It's the oxidizing agent. Oxygen is an oxidizing agent. Carbon is being oxidized. That would be the reducing agent, CH4. Here, carbon had how many oxygens bonded to it? None. Over here, it's got 2 oxygens bonded to it. In organic chemistry, the definition of oxidation is an increase in carbon-oxygen bonds. Here it went from not being with oxygen to being with oxygen. The carbon is getting oxidized. That goes back towards the origins of the word oxidation. So let's do this. Write a balanced equation for the complete combustion of liquid C2H5OH. Anybody know the common name for that? How many carbons? 2 carbons, right? What's the prefix that means 2 in organic compounds? Mom eats pickled bananas. Methanol, ethanol. This is an alcohol with 2 carbons. It's ethanol. That's the stuff in like vodka and whiskey. It will only kill you slowly. Other alcohols like isopropyl alcohol or methanol will kill you much quicker, and they're not nearly as fun. So we don't have to identify oxidation or anything, but we just need to write the balanced equation. So here's our reactant, C2H5OH. Doesn't specifically require state symbols, but let's practice. That's a liquid because it says so. That's all they gave us. With the word combustion, oxygen. So our other reactant is oxygen, O2. What state is oxygen in at room temperature? It's a gas. Okay, so there's our reactants. What are the products? CO2 and H2O. So this is burning. What do we think the temperature is? Is it going to still be room temperature? It's probably going to be hot. So let's assign our state symbols based on it being pretty warm. So they're both going to be gases. Now we have to balance. I like to start with carbon and then hydrogen and then oxygen. You want to leave oxygen for last because we have oxygen as an element here, so we can change that without messing up something else. So over here I've got 2 carbons, and on the right side I only have 1, so I'll put a coefficient of 2 in front of CO2. Then we'll look at hydrogens. Be careful over here. There's 5 here, and this guy's over there. So there's a total of 6, and I have 2 over here. If I put a 3 in front of water, I'm good. And now I have to deal with the oxygens. So I want to count up all the oxygens on this side. 2 times 2 is 4. So I've got 4 plus, each of these has 1, and there's 3 of them. 4 plus 3 is 7. And over on this side, I've got this guy. This is where I'm wanting to put the coefficient. There's also 1 oxygen hiding over there. So I've got 1 plus something, And I need that to be 7. So this number needs to be 6, right? So I need a 3 in here. Questions?
Why'd you put this, how did you know automatically that O2 goes right there?
That O2 is a reactant? Because it's combustion. The other reactant in a combustion reaction is always O2. Any other questions?